almost there. We're going to take this 89, oops, let me get a different color. This 89 volts per meter, 89, that made it into the brain, and see how that dissipates. Let me get a new sheet here. Scroll back up. Oop, I guess I have plenty of space at the top, so I'm just going to start up here. So we had 89 volts per meter, and we want to find how does that decay in the brain. The FCC limit, if you remember, is one allowed limit of 1.6 watts per kilogram heating, averaged over 1 gram. Okay. The area of our plane wave, which we determined earlier, which is the area of half of the cell phone, is this. The area is 3.4 times 10 to the minus third meters squared. That's one piece of information we know. The second piece of information we need to know is the brain density. Brain density, mass density. And that is, on the web, 1.05 grams per cubic centimeter, roughly. Which is not too surprising, because this is about the density of water. Water is 1 gram per cubic centimeter. Same thing. Your brain is mostly water. Okay. What else do we need? We need to calculate, because we need to average this decay over 1 gram, how much brain mass is involved with, how much volume is involved with 1 gram of brain mass, and what's the thickness of that volume given this area. So let's write it out this way. So 1 gram equals 1.05 grams per cubic centimeter. I'm going to write it as centimeter cubed times 3.4 times 10 to the minus third meters squared times thickness T, which is in meters. This is the volume. This is the mass per unit volume, for volume. And this is the mass. Okay. We want to find T. We want to find this guy here. Okay, let's run through the calculation. 1 equals 1.05 grams, 1 gram per centimeter cubed, times 100 centimeters per meter, because I want to convert to meters, quantity cubed, times 3.4 times 10 to the minus third meters squared times T. I'm going to assume you can do the math there, and I'm going to show you that T is equal to, or approximately equal to 0.00028 meters, which is equal to 0.28 millimeters. That's our thickness. Okay. We take that thickness and we're going to draw this little model of what's going on. Impinging, we have on this volume, we have 89 volts per meter. We have a distance here of 0.28 millimeters, and then exiting, we have some unknown electric field. The electric field that comes out is going to be the initial electric field times the exponential raised to the power of 0.28 divided by alpha, times alpha. That equals 89 times the exponential of 0.28 times, and you'll have to think back and trust me that the attenuation coefficient is 9 millimeters. Divided by 9. Right. Alpha is 1 over 9 millimeters. Okay. 0.28 divided by 9 millimeters. I apologize for things getting a little sloppy here. That is equal to 89, or approximately equal to 89 e to the minus 0.0311, which is approximately equal to 89 times 0.969. There's not a lot of absorption that happens here, and that equals 86.2 volts per meter. So this E is 86.2 volts per meter. So the delta electric field is 89 minus 86.2 volts per meter, which is equal to 2.8 volts per meter. That's the decay of the electric field in that volume. How much power is involved with this decay? Delta P equals 2.8 volts per meter squared divided by the characteristic impedance of that medium, brain, which is 50 ohms, which is 0.16 watts per meter squared. Almost done. We have watts per meter squared. We just need watts. Okay. So, and this is the amount that decayed over 1 gram. So we need to multiply that by the area of the plane wave, 0.16 watts per meter squared, times the area of the plane wave, 3.4 times 10 to the minus third meter squared, equals 5.4 times 10 to the minus 4 watts, and I've dropped a unit here, but watts per gram. Okay, that's not what we need. Oh, let me leave it here. We need watts per kilogram, so we need to convert that 5.4 times 10 to the minus 4th watts per gram times 1,000 grams per kilogram equals 0.54 watts per kilogram. Let me write this in a different color, which is less, oh, it's not a different color, which is less than the 1.6 watts per kilogram recommended by the FCC. That means it's safe. Cell phones are safe. And in this calculation, I included enough margin that as long as my numbers are even remotely close to reality, that the cell phone actually is very safe, because remember, I made the assumption that it was emitting twice as much radiation as it actually does, and I was making the assumption that we're dropping the electric field over a much shorter distance than would actually occur in the brain. So, assuming that the FCC is correct in saying this is the amount of power that's allowed to be dissipated, cell phones are safe. And I'll make a note that the most power per unit volume is going to be dropped in the first little section of the brain, and after that it's going to decay exponentially. And so doing this calculation for the first gram of material, the first little bit of material with whatever volume it turned out to be for that area of the plane wave came out to be the 0.54 watts per kilogram, and that's less than 1.6 watts per kilogram, and so cell phones are safe.